Welcome to the Deep Dive. Today we're plunging into quantum computing. It's this fascinating field, really forward-looking, kind of reshaping what we think is possible. You probably know how a normal computer bit works, right? It's like a light switch. Simple, either on or off, a 1 or a 0. But imagine a light switch that could be on and off, or even somewhere in between, maybe all at once. It sounds impossible, I know, but that's sort of the basic idea behind a quantum bit or qubit.
Exactly. And it's more than just, a weird physics concept. This tech really promises to solve problems that are just completely out of reach for even the best supercomputers we have today. It really sets the stage for some potentially revolutionary changes.
Okay, right. Let's unpack that a bit. So it's not classical bits, these qubits. What's really going on there? How do they actually behave differently to give them all this power?
Well, the first really key difference is something called superposition. Unlike that classical bit, the simple on or off, a qubit can actually exist in a combination of states, both 0 and 1, at the same time.
Both at once.
Yeah, kind of a blend of possibilities until you actually measure it. And this means a quantum computer can handle a huge amount of information simultaneously. Think about it. Just adding a few qubits increases the processing power exponentially. It's massive.
Exponentially. Wow. And there's another piece to this puzzle, right? Something called entanglement.
Ah, yes. Entanglement. It's maybe even stranger, sometimes called spooky action at a distance. Basically, when you entangle 2 or more qubits, they become linked, deeply linked. Whatever happens to one instantly influences the other, no matter how far apart they are.
Instantly. Like no delay across any distance.
That's the idea. It's like having 2 linked coins. You flip one here, the other one, maybe miles away, instantly gives you the opposite result. It allows these computers to perform incredibly complex calculations across many variables all at once. It's parallel processing on a scale that classical computers just can't touch.
So they're connected, performing linked calculations.
Exactly. It's not just doing one thing faster. It's like exploring countless paths simultaneously.
Okay, this is where it gets really interesting, I think. Beyond the kind of mind-bending physics, how does this actually translate? What are the real-world breakthroughs we might see?
Oh, the potential applications are huge, really transformative. Take drug discovery and materials science, for example. Imagine being able to simulate molecules with perfect accuracy, predicting exactly how they'll interact. You could, design a new drug atom by atom instead of years of trial and error.
Wow, so bypassing a lot of the slow lab work.
Precisely. We could engineer brand new materials, things like maybe room temperature superconductors, or design super efficient catalysts for chemical reactions. It's really about building things from the quantum level up.
That's pretty amazing. And I've heard it also impacts something really critical today, cryptography, or digital security.
Right. That's a big one. There's definitely a challenge there because, yes, a powerful enough quantum computer could potentially break a lot of the encryption we use today.
Okay, that sounds concerning.
It is, but it's also pushing us to develop new kinds of encryption, quantum-resistant cryptography. So while it poses a threat, it's also driving the innovation needed to safeguard our data in the future. It's sort of an arms race, but one that should lead to stronger security overall.
Right, so a challenge and an opportunity there.
Definitely. And it doesn't stop there. Think about artificial intelligence and machine learning. Quantum computing could allow for much more complex AI models, processing data in ways we can't currently, potentially huge leaps in AI capability. And then there's logistics and optimization. Things like figuring out the absolute best routes for thousands of delivery trucks globally, or managing incredibly complex supply chains, or even modeling financial markets.
Yeah.
These problems have, a mind-boggling number of variables.
Problems that just bog down current computers.
Exactly. They just hit a wall. Quantum computing offers a way to find efficient solutions for these massive optimization tasks.
It really does sound like we're tapping into some fundamental rules of the universe to get things done. But if it's so powerful, why don't we all have quantum laptops yet? What are the big hurdles?
Yeah, that's the crucial question. We're still quite a ways off from large-scale, practical quantum computers. The main challenges, well, these quantum states, superposition and entanglement, they're incredibly fragile.
Fragile? How so?
They're super sensitive to their environment, tiny vibrations, temperature changes, stray electromagnetic fields. Any little disturbance, what we call noise, can make the qubit lose its quantum properties. It just collapses back into a classical 0 or 1. This is called decoherence.
So keeping them quantum is hard.
Extremely hard, and scaling up, adding more qubits while keeping them all stable and interconnected, maintaining that coherence, that's a massive engineering challenge. But, the progress being made is actually remarkable. There's huge investment globally from governments, from major tech companies. Everyone sees the long-term potential.
So wrapping this up then, the incredible power we're talking about really comes down to harnessing these almost weird quantum effects like superposition and entanglement.
That's the essence of it. And maybe the final thought to leave you with is this. Unlocking these quantum secrets, it really promises to redefine what humans are capable of. It could genuinely usher in an era of innovation and problem solving, unlike anything we've seen before, shaping our future in some really profound ways.